Hi, good morning everyone. Good morning. Welcome to our session. So I am Bertrand and this is Emilia. So we are math teacher from the French school Georges Pompidou, which is just next to this building. And today we're going to talk about how we use in our school algorithms to improve children's math skills. So sorry, we have to switch the mic when we
So in fact, we program algorithms in our system. So first of all, sorry for our English. We teach in French. We speak all the time in French. So we hope we won't make a lot of mistakes in English. So we use to program algorithms in our curriculum since 2009. So it's not new, but it's quite new. And then at the end of the session, if we can speak with you if you want about the difficulty we have at the beginning to introduce algorithms for the student and even for the teacher. We never have taught that before. So now in our curriculum we have to make some programmation of algorithm and we use it a lot. And then in our final exam, French baccalaureate, there is some question coming at the final exam and then the student has to be prepared to answer to this question too. So first of all, we have to try to, we think that for the students to make algorithms, help them to organize their thinking. We take a very easy example here. For example, the question was, create an algorithm that calculates the side of a rectangle triangle. It seems to be very easy when you do on paper, but when you have to do that on the computer, it's not so easy. You have to think how I will make this calculus. You have to think, do I need to calculate the hypotenuse or the two other sides? And in fact, when you do algorithms, what we observe is that the student needs to think step by step. And for us in math, to have this way of thinking is important. When they have to solve a problem, they don't know to give immediately the answer. Sometimes to go to the answer, you need to go step by step. And with algorithms, you're forced to do that. And then it makes the student understand the interesting on doing like that. And second point that it is interesting, some students, not all, we'll speak about that later, not all, some students have difficulty with algorithms. Some students are more motivated to make algorithms that to solve a problem on paper, just because they like to see it working. And then they enjoy to see the result. When they do the same problem on paper, they don't care about the lines of the hypotenuse. It's 5 or 4, doesn't matter. But to see something work is very important for them, and it's working like that. So that's the first point we want to share with you. So now,
And another example is that when we use algorithms, it also helps them to learn their lesson, basically. If you ask someone how to solve a quadratic equation, very simple one, ax squared plus bx plus c equals 0, everyone has done that before, but it's very easy to program on a graphic calculator. But in order to do that on the graphic calculator, it implies that you have to know the background first. So if you want to do the algorithm first, you have to learn your lessons. So the final product on the calculator is very enjoyable by the children because it ensures them that they are not miscalculating the discriminant and then to have the right solution at the end.
So a lot of programs we make during our classrooms, one objective is that the student can reuse it after it, not during only one lesson. And then one other good point is that when you make some algorithm programmation, you can make more strong conjecture than you did before on paper, because you can make a lot of simulation, you can have a lot of results, and then be confident of your result. And for us it's very important, because in fact when you have conjecture, it's just to have an idea of the problem you try to solve. And to have an idea is a lot of time a good way to start to solve a problem. So we observe that our students, when you give a problem to solve, sometimes have difficulty to start it. And when they make a simulation, algorithm, or whatever you want, they have an idea of what to prove, and then it helps to start. It doesn't give you all the answer, but it gives you some direction where you can go. And we find that it helps them to start program. We put an example, for example, that Bertrand will explain to you, the Montreal game. I don't know if you know it.
So just to take back what Emilia said, when they have a problem to solve, either they don't have any idea to how to solve the problem, so they are blocked, they cannot proceed, or they have an idea, but they are ashamed to start with their own hypothesis because they don't know if it's going to end right or wrong. So use the algorithm. It's a good way for them to quickly see if their idea is going to work or not. And then after that, they can start to solve their problem. For example, the Monty-Hall game, I don't know if you know about that game. There's 3 doors. Behind one door there's a car, and behind the 2 of the doors there's a goat. The one who's playing has to choose one door, and the presenter is going to open, he knows where is the car, so he's going to open one of the door which there's no car behind, and then he's going to ask the one who's playing the very simple question: do you want to keep your first choice, or do you want to change to the other one? So what do you think? Are you going to change, or are you going to keep your first choice? Why? We have to switch. Right, that's right. Because when you switch, you have 30% more chance to win the car when you change. It doesn't mean you're going to win, but it just means that you have more chance to win. And to explain that to children, it's very difficult. But when you run the simulation several times, then it gives the children the idea that this is the right solution. And after that, we can start to make the math on papers.
So So we observed that when we make algorithm, it was a good surprise. Some new mathematical questions come to you. For example, we take a very simple example, what we call the Syracuse conjecture. It's very simple. When you have a number, you multiply it by 3 and add in 1. And when it's an even number, you divide it by 2. And if you continue for a long time, it has to go to 1. It's not proof now, but it will go to 1. So you can ask the student to try to try this conjecture, but at what time will come a simple question: what is an even number? Oh. So all the students will say, oh, it's a number which finishes by 0, 2, 4, 6, or 8. Okay, explain that to your program. It's difficult. You have to find another way to explain it. In fact, and some you can explain that it's better to divide it by 2 and to round it, and if it's the same result without rounding the number, it's an even number. So it's bringing some new question you don't have in a classical exercise. And what you will see is that some other students are better than the one they used to be in the classical math lessons. Is that okay? Then Bertrand?
And also we've observed that by using algorithm, it develops with the children logical skills as well. For example, when you ask the children just to order 3 different numbers, A, B, and C on paper, it's very easy for them. But when you ask them to program, to do the algorithm on the computer, it's a more challenging task for them, because it's very difficult to tell a computer how to order 3 different numbers. So on paper, it's very easy to do it, so it's not a mathematical difficulty, it's more algorithm difficulty. So we don't want to mix that all same together.
So what is interesting is that you can make some work on logical skills without too much math. And sometimes for some students, sorry?
Use conjecture.
Yeah.
It's more clear.
You just pick one number, and if it's odd, you have to multiply it by 3 and add 1. And if it's even, you have to divide it by 2. And you start over again and again and again with the number you choose at the beginning. And every number you pick, you end by 1.
But it's not proved by mathematicians.
It's
easy to try, but very difficult to prove. And so it's interesting, example, we put it because it's interesting to show children, it's not our subject today, that there is something to prove, still to prove in mathematics. Not everything is proved now. So this seems to be very simple, because the proof, I think, is not fine. So now, yeah, what is to be rigorous? This question is very difficult for our children. What we mean by be rigorous in what you say and what you write. When you come to them, I explain them that the result they find is good, but the way they find it is not okay. For them, it's difficult to understand because the result is there. Why you want to see everything before? With the computer, it's different. If there is only one mistake in the middle, the computer will stop the program and it won't continue. And when this problem comes to them, often what we do with Bertrand is that we speak, look, here, you take care about every line. Why do you do that with the computer and you do that with me? I will appreciate if you can do the same when you solve an exercise, is to be at each line, you take care of what you say and what you see. Second problem is that sometimes the program works, but the answer that is given is wrong. But we like that our student verifies that there's a solution. But when you do that on paper, it's difficult to verify because you have one result. And it's not so easy to see that the result is strange. When you do that on an algorithm, you can try it a lot of time. And when it's a lot of time going strange result, you can see that there is something strange and you have to find the solution. And to find the solution, what is interesting is that the student has to come back to the algorithm step by step again to check every line what he is doing and why it's not working. And it's exactly what ones that they do, when his solution is not good, they have to check what they are doing and understand what those mistakes could be. So the way they are finding an error in the algorithm is similar to what we like they find their mistake in their own production. So there is some parallel between the two things. So abstraction. This is difficult. Our student, it's not so easy to solve abstract problem in maths. There is one way to try to help them with that is that often as teacher we try to find real life situations that illustrate the abstract problem we want to solve. It's a good way to do it. It's a teacher way to do it. But sometimes, even as teacher, it's not always possible. But think about the student, when they have an abstract problem to solve, will they find alone a real life problem that illustrates the problem they have to solve? It's not so easy. Because when we come into our classroom to illustrate an abstract problem with concrete situation, we think a long time about it before, to be sure that what we speak about will well illustrate the abstract problem. And what we observe is that some students use by themselves algorithms to better understand the abstract things. For example, for sequence, we want to understand the behavior of a sequence. Some students immediately, by their own, take their graphic calculator to make a program and try to see how it's working, what is the next number, and then to better understand what the sequence is. We don't go to a concrete number with concrete situation with this sequence. It just helps them to see it working. Even with limit, it's something difficult for students to understand because when you show on the screen a function, you just see the function in a little square and you're speaking about infinity. When you go on algorithm and try to see what's going after, they can put 1 million if they want. They will have an answer. Is it possible that the function go more than 1 million? The algorithm can do it. On the graphic, it's useful sometimes, but for some of them it's difficult because you see, you speak about infinity, but you show me the function between 0 and 100. And we're speaking of 1,000 million, etc., etc. Some of them lack to do that by themselves, not whole. And that is another point. Algorithm is a good tool, but it's not the ideal solution to solve every problem in math. It's just a new tool we can use. It won't replace other tools. You still need to use paper and math to search a problem. We don't want... Sorry.
Okay, so we use algorithm in our school. So we want more and more children to come to our class and use algorithm. But it's not that easy to bring students to do algorithm. So we have to use several tools. And we cannot do the work in algorithm in 1 year. It's a really progressive work. It cannot be done in 1 year work. And as I said earlier, we have to be very careful not to mix mathematical and algorithm difficulties all at the same times. For example, when we use Pythagoras, they learn Pythagoras very early. So we can take back this theorem and try to do the algorithm on that later. They know the theorem, but they're going to use the algorithm to illustrate the Pythagoras theorem. So in order to bring students to do algorithm, we use also 3 other tools, which is Scratch, Lego, and the Beaver Challenge, which we're going to talk just right now.
So first of all, what you need when you make algorithmic with students is a software which is quite easy to use. We use at the French called AlgoBox, but it is in French, and we use also Scratch that you can find for free in English or whatever languages you want. It's important that it has to be free. That means that your student can download it at home and try it if they want it, because it's our philosophy. Nothing expensive for the student. It's very easy because you have everything here on the left, and you just pick up and build your algorithm. And because you pick it up, it avoids a lot of little mistakes you make when you start algorithm. For example, if you write a program like on a written program, A times B, on paper you write AB. If you write on the computer AB, you think it's a new variable AB, it's not A times B. With this sort of program, you won't have the problem. So it avoids a little mistake that is difficult for the teacher to find. It doesn't work. You go to the program, you don't see the mistake, just because they forgot a times. Other problem, when you have condition, if A equals B, a lot of languages use 2 equal to compare the two numbers. If the student forgets to do that, it's very difficult when you go to see what he was doing to find it. This sort of software avoids this problem. So if you start to make algorithmic, it's for teacher also a good thing to be sure that we won't have some little mistake. And it's very useful to use. I won't speak about it more, but find a good software for that is very important.
And also, for example, when you do a loop or if condition, usually you have to end the condition at the end. So, and with that, it's very easy. When you snap the brick on the left side to the right side, you start the loop and automatically it closes the loop at the end. So they don't have to worry about making mistake in the syntax.
So, second thing we use, in fact, we make all our students, middle school and high school, making what we call the Beaver Computing Challenge. We put 3 little beaver from different countries, depending on where you come from. If you go on Google, or you can find a lot of beaver challenge everywhere in the world. Why we are doing that? In fact, in the middle school, there is no programming of algorithms in our school. But we find that when they arrive in the high school, they are surprised at the beginning to see math teacher doing algorithms. And with this computer challenge, it's organized by the math teacher, and we want that the math teacher organizes it. And when he's coming to the middle school, he used to, every year to have a challenge, a computing challenge for everybody that the math teacher organizes. And when they arrive in the high school, they're not surprised that we are doing that. They know that math teachers are interested by computing. The question, everything is online. You have nothing to take care about. Everything online, everything is correct online, it's very easy to organize. The only difficulty is to have a computer room that you can use during 1 week. And the student doesn't need to know how to write a program. The challenge is only based about logical skill that we need in algorithm. For example, here we have 2 points all the square. We make a little program here, you know, it's 3 times 2 south and 2 east. It's very easy, it's not difficult to program. And then when you are online, you can start the program and you paint and you can see what happened. The best is to paint everything. So we use that just to, that student knows that as math teacher, computing is a part of our program. And then we use another tool for
Sorry.
the,
that's the link. The links that
can come back
brings
after
you to the Beaver Challenge. What we use also for the first year, this year, with the secondary children, is to use the Lego Mindstorm. I don't know if you've heard about that. Basically, it's just Lego bricks, and you have a brain here, and you have several sensors on the edge. And when you build the robot, you can program the robot and try to make the robot do what you want it to do. So it's very easy and progressive tools we can work with to introduce algorithms to secondary level children. There's a possibility to bring new students to do algorithm by using that because it's fun and it's easy at the beginning. There's a possibility to involve during the project. For example, when you start with the children who doesn't know what is algorithm, is gonna have some difficulties to see and to try to do the algorithm. So you can introduce that to him. But also some students know already about algorithm, so they want to do more. And with the same group, you can work with both of them. And finally, the students are very proud of their product. Usually, when we do math, at the end, there's just the results, and that's it. And it doesn't mean that much to them. But when they have a final product and they see the product at the end finished and work, they are very proud of the product. And that's what they've built in 8 weeks. I'm just going to show you the short video here. Sorry. So first of all, they have to to get used with the Lego bricks, they have to build the robot. So the first project was to build a soccer robot. He has to find the ball, see the ball, kick the ball, and eventually when he arrives in front of a wall, he has to go back and turn and try again to find the ball. So the first part is the build, and then there's the wiring, and then when the wiring is done, they have to go on the computer and do the algorithm and download the algorithm on the robot. And then they have to test the robot if it's working or not. I'm just going to show you the video where it's working, but there was several videos before where it was not working. So you just find the ball, when he sees the ball, he kicks the ball. The first one was kicking the ball on the front, and this one is kicking the ball on the side. So different point of view. And for those who have done that very quickly, they can move to something else. When they see the wall, they stop, and they go back, and then they try to find the ball again. I don't know if you have seen, but the ball is square. It's better for them, it's not moving so fast. And when the project is done, what we do is we put the children outside the classroom. That way they can show their project, they are very proud of their project, they can show their small robot to other children. That way the other children are amazed, and then maybe they can come back to us at the next session.
And there was a funny thing during this day, because the robot were well working in the classroom, and when they go outside there was a lot of sun with the light, and then because there is a light sensor in the front, it was too much light, and then the robot doesn't see anymore the ball. And Bertrand has a good reaction. He said, look, when you use a theorem, you need some condition to have to use it. We lost the condition outside, that's why it's not working. It's exactly the same we want in math. You want to use Pythagoras theorem, you need a rectangle triangle. You don't have a rectangle triangle, you cannot use it anymore, Pythagoras. So he make a comparison with math. It was not, it was unexpected.
Yeah, I wasn't expecting that.
Well, so they don't play very well football. It's like a French team now, but we expect that with years they can play like Brazil. I don't know. It's a worldwide cup now. So then last things.
Sorry.
So we want to finish that because we speak about students using algorithms, but you can as teacher use algorithms to help to understand things to the student. For example, in France, we try to explain to our students what is a confidence interval. It's not so easy to explain to students. So what we are doing is that we explain to them, we take a square, and by chance some dots are coming. Either in this quarter circle they are in green, either here they are in purple, and the proportion of green is by little calcul like to find pi. But if you try to make the simulation, and then you can see that for the Scratch you have a very good site, scratch.mit.edu, where you can find a lot of algorithms that some teachers have done, and then you can take it back without losing time to program it by yourself. Then you can see, we make a 500 simulation, the dot coming, and then Bertrand will stop it now, and you find 3.16. And then you tell your student, do you think if I repeat this experience, I will find the same result? And you say, no, it's impossible, so we will do it a second time, because there is some chance inside. And you see now, we find 3.16 the first time. The second time we will find, I don't know why it's suspense. If I find the same one.
There you go.
So 3.19, and then you ask the question, so what is a good number to give an estimation of pi? And they say, we don't know, it will change a lot of time. And then we explain to them, look, instead of giving one number, why we can give an interval where there is a lot of chance to find pi. And then we introduce the notion of confidence interval. And then we use algorithms to explain them something. You know, we speak about Montiel at the beginning of the session. There is one thing, if you don't want that your student programs the algorithm, you can use it, we can find on the same site. And then you can start the program.
So basically what we're going to do here is to make several trials to this game and to see if, when we change, if we have more chance to earn the prize at the end, or rather than not to change the change.
So we put, for example, 100 trials.
Oh, sorry, it's in English. So we're going to switch answer.
And speaking time 0.
So it's going to run all the simulation.
And then it will run by himself 100 simulation. And then instead of making your student make the program, you can show them how it's working. And then you will see that when you switch, you will have around 66, what was it for me?
Percent
Percent of result. wow, I have a lot of chance. And then you can repeat this experience without switching, and you will see it around 33.
Still 100.
So
We don't
it's
want to
important
switch.
for us it's a good tool for us. A lot of time we use that, and this site you can take the address, we say in English, I don't know. It's very useful. There's a lot of programs that are very well done and very useful.
Switch rotation.
Yeah, and then when we don't switch the door, the result at the end is only 30%.
Around this
Around.
simulation. And then we don't speak about that before. Algorithmic is very useful in probability because you can run a lot of simulation, and sometimes they understand that there is some difficult program we cannot solve on paper, but we can have an idea with simulation. So, to make a little conclusion, I will give the Bertrand.
So finally, here to conclude our session, we strongly think that using algorithm, it's going to bring back the student to math, and make them to do math with a better mood. But we have also to be very careful not to overdose those who don't like algorithm but still like math. So we have to keep a balance between those who like it and with those who don't like it.
So we think it improves their skill. We hope that we convince you during this time. And then the last thing is that, you know, there is algorithms everywhere. And then we speak during the conference, we speaking about relevant before. You move with the time when you speak with algorithms. There is everywhere, and it helps them to understand how it's working algorithm. And they like it because it looks like to be modern. And for our students, they like when things are modern. Pythagoras is fine, but it's a long time ago. Doing algorithm for some of them is very cool. But like say Bertrand, not all the students. Some of them don't like it. So we have to be very careful.
And we have seen during all the presentation that it also strengthens and improves their skills in math during algorithm.
So we're
Thank you very
done.
much.
You just move with the time.
Yeah. Oh.
With the times needed.
Oh. I mean,
It's an expression. It's just in the world we are now, there is algorithm everywhere. And it's interesting to explain to students what is an algorithm and how it's working. When in every product we use now, there is algorithm inside. So they like this idea to see we are trying to explain in which world we are living in. So for them, when we saw our students, some of them like it because just by the idea it's speaking about our time. When you speak about Pythagoras, some old mathematician, for some of them it's not so fun that when you make algorithms, not all. So it just
and they don't really see the meaning of what they are learning. So by also doing the algorithm at the same time, they think, and it's also right, that we are more close to the real life using algorithm.
But as we said before, algorithm it's a tool. It's not the only tool we have to use. Paper sometimes is better than algorithm.
So you are making the students to make the algorithm?
Yeah. Our objective is at the beginning when we start with them to start. We are very satisfied when by themselves they think that they can make it by their own, that they find that useful by themselves and to start an algorithm by their own decision. But it doesn't come the first day. And you will see in your classroom that some of them like to do that, and some of them who have difficulty to prove something can be very good in algorithm. And then when you give a problem, they don't search the same way than the other, but they can start a search. And you know, we speak about the pivot challenge. It's very interesting to see the result. It's not the best of the classroom in maths that we won the challenge. You have another order of student, and then it gives some confidence to some of them because they see that they can do good in maths because it's a different way to do it. So it's different. It's another way to teach, but it's during our classroom. During a week, we don't make algorithm every lesson. It's sometimes one time during the week. It's like we say, it's a tool. It's not the only one. The danger of that is to want to do that at every time. Sometimes what I repeat, when you make space geometry, it's better to see the object in reality than to put it on the screen because it's still two-dimensional. So we don't want to leave the impression that it is the tool of math. No, it's one tool, and sometimes we don't use it during 2 weeks because it's not useful.
But as they grow, at the beginning, we just present them the algorithm, they just have to run the algorithm and see the results. But more and more when they grow up, they have to do their own algorithm. And finally, what we would like to do is that at the final year, they are able to have a problem and try to solve it first with the algorithm and then come on paper to do it on themselves. Other question? Okay?
Thank you.
Thank you.
So can you show the website links?
Yeah, of course. Yeah.
Which one?
All the three.
For the beaver?
Yeah.
No, all we can solve
There
it.
was one slide.
There was a
This
slide
one?
with 3
The slide
links.
with the
Ah,
website.
okay.
All right.
You said it will come back to.
Montre-moi.
No.
One?
Website.
Hold on. I knew.
But the other side for MIT is very interesting, in fact, because when you're not, sometimes there's some difficult algorithm to write, and if you,
CMC is also very good. CMC.
yeah, all are, in fact we use this one because it's in French, but you can on the French one you can try the challenge online even if it's not in a number. We didn't find how to try the other one. It's you can find the former exam but in PDF. It's not the same because it's more. And you know, for the challenge, you have 1 week to do it. In fact, so you don't need that all the students do it at the same time. Yeah, in fact, you have to register in October, and then you go online. As a teacher, you don't have any.
Does it have simulations?
Alors, in fact, the French one, yes. So there's some teachers that can do the difference, yes. The two others, my English is not so good, so perhaps if you go on the site, you will find the links and go to simulate and you will see it paint, and if it's working or not. You can try and repeat a try. If you go in PDF, you write, for example, the answer, but you don't see it working. So it's very. You can try to make the French one to see how it's working online. Even if you don't understand the languages, you will see how it's working, I think, quite easy. And then after it will be the same online for the British and the Canadian. But there is an Irish version also in Google. And the contest is for 45 minutes. So it's less than a period. And the students like it because there is 10, 18 questions. Some are very easy and some is going fast. Those are the feeling not losing their time. And then you have some difficulty questions to make them rank, order, etc. And then you have a national ranking depending on the challenge.
Yeah, but those are the regular challenge questions. It doesn't need algorithms.
No, you just need to be logical as algorithm. You have no program. It's in this contest, student doesn't need any.
They don't.
Even when our sixth grade, they do that the first time, and they have no problem. We don't ask to put if, then, etc. Just a sort of logical to have, which is sometimes different that we can find in other challenge. So no, you don't have problem with that. You see, for the painter, alors tu peux mettre le, c'est où les robots peintres ici? So this is the online version, and for example, we can make our program here. Put I don't know what 3E. Non, c'est en anglais.
3D, 2D, so west.
And then you're online and you can try the program.
No.
I don't understand you. Yes, because you write in English, it's 1 O.
Oh, sorry.
And whereas S is the.
Okay, right. There we go. That's
Okay.
it.
And then the students can see and change the program and see if it's working. So that's the online version. But I didn't find the English one online. I don't know why. But I'm sure you will find it because. And then you have, and you will see what is interesting with that is that you. The rank of the student is very will surprise you. And that's a good point because the student you think is average can be very, very, very good. And for when then you come back to him and say, look, what you can do is very interesting. So just take confidence, learn perhaps better your lessons, and you have the logical with you. It's just a question of how to use it. And then we have a lot of students who are very proud of what they are doing here, and they are proud to be better ranked than they use. We don't use rank at the STEM, but they know they're great compared to the others. So it's 1 hour per year. We organize it since 3 years, and now it's the student asking us when the channel will be. Other questions? Okay, thank you for your attention. Have a good day.